So, having just talked about diffusion, we are going to then apply that to some specific diffusion of certain things here coming up in this chapter, like sodium and potassium ions and that kind of thing. We're going to talk about what if you have a situation where they aren't just free to diffuse by themselves, but something else has to be involved, like carrier molecules and that kind of thing. So we talked about, like in the case of osmosis, if you set up a gradient, to go back a slide, if you set up a gradient where there's more water, a higher concentration of water on this side than that side, the water naturally wants to move from this direction over to there, and since you have the same starting volume, that means less of this is water and more of it's made up of solute. More of that volume is made up of solute, so there's a higher concentration of solute particles here. They're going to want to move back the other way. Well, what if you have a membrane that allows water to move but does not allow your solute to move? Well, the water is still going to diffuse in that case, and then it'll move over here, and what you'll see is this happening. Okay, you'll see that water level rise. Now, what controls how high it rises? Has to do with pressure. Okay, even like atmospheric pressure and that kind of thing, because it's going to continue to rise so long as the pressure being exerted by the atmosphere, for example, isn't too much. It's going to stop rising whenever it sort of comes in equilibrium with the amount of pressure that it's feeling on this side, and that's going to keep it from rising anymore. Okay? Now, you can also go back, take this back down to this dotted line and make them even again before we start. And you can, like, say this was a cylinder that you could fit a piston to. You could fit a piston to this side right here and create pressure and push down on this. If you were measuring this pressure, you've heard of, where I'm going with this is you've heard of osmotic pressure before maybe. If not, it's no big deal. But osmotic pressure of solution is how much pressure would you have to physically apply to prevent osmosis from happening. Okay? You could actually force. Imagine taking this and shoving it down and actually physically backwashing these molecules to the point where they can't freely move now where they would want to move because you have forced them to not be able to do so. The amount of force that it would take, the amount of pressure that it would take to oppose osmosis is called the osmotic pressure of that solution. Don't worry about that. Okay, now anytime a column of water starts standing, starts to increase in height, realize that you build pressure. The higher water is, the greater pressure you experience. If you don't believe this, it's a difference between going underwater in a shallow end of a pool versus going 10, 12 feet underwater. You can feel the pressure difference. The farther down you go, the more water is stacked up on top of you, the more pressure you feel. So when this hydrostatic fluid, or this hydrostatic pressure that you see here is because of an increase in the amount of water present, standing, like for example, in this column. You'll see when we get into like the nephrology, we get into kidneys and that kind of stuff, these kind of pressures and these gradients become very important to control where the stuff goes, okay, into or out of the tubes that are inside the kidneys. Okay, this brings us to something called tonicity. It's actually pretty simple. Do you remember ever talking about hypertonic, hypotonic, and isotonic solutions? If not, again, it's not too bad. What do you know what these prefixes mean? What does hyper mean? Above, excessive, too much. Hypo is the opposite of that. Iso means equal. Okay? So just apply that, and then you've got situations like this. If you have a cell, for example, let's look here, a cell in what's called an isotonic solution. What that means is, now remember, I'm talking about a solution. So that means what's going on, the iso comes from, the prefix is going to come from what's going on in this solution outside this boundary of this cell. Say you have a cell, and let's say these little orange dots represent solute particles. Okay? Here you have 1, 2, 3, 4, just an arbitrary number. Here you have 1, 2, 3, 4. You've got the same number of solute on either side of that cell. Is there a diffusion gradient in that case? No, nothing's going to move, right? Iso, it's equal on both sides. We call this type of solution an isotonic solution. Okay? In this case, the solution is isotonic to the cell is isotonic to the solution that's around it. It's an isotonic solution. Now, consider this one. Obviously, here you have a whole lot more solute particles on the inside of this cell than you do the outside. So these solute particles, if they could move, what direction would you see them move? Out of the cell, right? Okay, but in actuality, those things are usually controlled very much by the cell. However, what is free to move is water. So if you have a high concentration of solute out here, think about the water then, how much water you're going to have in here percent-wise compared to what's out here. Which is going to have a higher percent water, the outside or the inside? If you've got, let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Say there's 14 solute particles. And let's say there was a total of 100 particles here. That means you would have a 76% water solution, 14% solute solution. Out here, you've only got 1, 2, 3, 4. So you've got a 4% solute versus 96% water. See the difference? So there's going to be more water, for example, here. So which way would the water go in this case? It would go in. There's more of it there's a higher percentage of water outside than there is inside, so it would go in. What you will see happen to this cell is it will swell up because of the rushing in of water. Okay? Hypo swells up like a hippo. Think of it like that. Okay? So hypotonic. Why is this called a hypotonic solution? Because the solution is hypo in terms of the solute particles. Look how few there are out here compared to how many there are in here. So this is called hypotonic. The cell will swell up as a result of that. An example of this would be like if you took a bacterial cell from the Dead Sea. You know the Dead Sea is over in the Middle East? One of the, the saltiest freshwater, well, if you call it freshwater, the saltiest inland area that we have. That's how they used to get their salt from those times. You take a big, open the surface area, let it evaporate, and you could get crystallized salt by evaporating the water from the Dead Sea. Let's say you took an organism that was adapted and used to living in those conditions, where naturally they're going to have a high concentration of salt compared to what we would have in our cells. That's what they're used to. Okay? What if we pulled them out of that and dropped them in a glass of tap water or a glass of distilled water, even worse here on, where we're at? What you would see is those cells would take in all that water because of the differences in the percent water concentrations compared to normal cells like we have. That water would rush in, they would swell up, and they would pop. Okay? And they would probably to the point where they would actually pop and die. Now, if you consider this situation an hypertonic solution, notice the difference. Hyper are too many. Outside the cell, there are too many solute particles compared to what's inside the cell. So that means there's a higher percentage of water where? Inside or outside the cell? Inside. So where's water going to want to go? Out. So you leave a cell that's kind of shriveled up like a raisin by the time that you're done. Okay? This would be just the opposite. That would be like if we took one of our cells, okay, and took a glass of water from the Dead Sea and dropped our cell in there, you would see that this would happen. Okay? Actually, water would leave our cells and they would shrivel up. So you can see then how extremely important it is to maintain this solute balance in our body, because the second it becomes hypertonic or hypotonic, our cells are affected. So it's huge that we are able to maintain this type of homeostasis in our body, and you'll see that that's where everything's going to feed into now, maintaining all these balances. Okay, now as far as membrane transport, we're talking about things that are like proteins, for example, that are on the surface of the membrane that can sometimes span from the outside all the way through the bilayer to the inside of the membrane and allow stuff to pass through or along or on them from one side to the other. That's where we're getting at here. Okay? Now, we are going to have assistance in this process. We have a lot of proteins that are on our channel that are going to assist in this. It's not like we just have these giant holes that are floating in our membrane that stuff can just fly through. Then there's no point. The point is that we can control it and decide what comes in and what goes out. We can have carrier molecules that are flipping. In other words, they grab onto it and they actually sort of just flip and turn around, and then what was once on the outside is now positioned on the inside. We can have them actually open and create channels which things can pass through. Changing its shape in general. You'll see what I mean in a minute. These are all just different ways that these things can act. You will see that all of this flipping and all of this stuff going on can be active or passive. It can require energy in the form of ATP, or it can just happen by natural means. It doesn't cost us anything. Diffusion just happens. All molecules are just moving. And they randomly go until they've evened out, sort of. That's passive. It doesn't require energy. This would require the use of ATP by us. You will see where this directly plays out here in a sec. Okay, so we've got some things to consider as we're thinking about how these things are interacting with our proteins on the surface of our cell membrane. We've got specificity. It's very specific. For example, if you have a potassium channel that allows the movement of potassium ions, that's all that's going through there. Other things can't pass through there. They're chemically specific and designed to bond to one thing. Saturation. How full are they in terms of how many of them are being used? You know, it doesn't matter if I have this ginormous wad of potassium that I need to move to the inside of the cell. It's not going to matter if I only have 10 channels to work with. That means I'm only going to move, let's say, 10 at a time, for example. It doesn't matter if I have 3 billion of them or not. So saturation becomes very important. And competition. Is there anything, for example, if I'm going to take potassium and move it to the inside of the cell, is there anything that's going to compete with potassium and hog those spots, cut in line in front of potassium, that will slow things down and cause it not to be able to pass as well? So all those are going to be important. Okay? So let's look at some that do not require energy. Some examples that will not require energy by the cell. We call this facilitated diffusion. Facilitated means to help, right? I'm a facilitator of learning. I can't make you learn it, but I can help you learn it. Okay? This does not require energy. It's a way to assist in this transport. Okay, so we still have this. Notice, from higher to lower concentration. We still got that same thing. There's no energy involved. So we still have to work with a diffusion gradient. However, the difference is, unlike simple diffusion, we are going to use a carrier molecule. Something's going to be involved. There's going to be a middleman. Okay. For example, glucose is a great example of how this works. Glucose, it diffuses across this normal gradient. There's a higher concentration of it in the blood than inside the cells, but it can't get there without insulin and other carrier molecules that actually can change conformations and move that glucose into the cell. It can't just float across by itself. Okay, here's sort of a very rough schematic as to how this would work. Let's say that here's our inside. Okay, here's our ICF, here's our ECF out here. Notice that you have a concentration gradient, high to low. In other words, naturally, if this was an open channel, these guys would just eventually want to diffuse in this direction. The difference is they can't. They are chemically repelled by these phospholipids, so they can't just wedge themselves through. You'll find that things like carbon dioxide and oxygen actually just go straight through. They just wedge themselves right between these little things and float across and to the other side. Possibly because they're so important. Oxygen has to get there. CO2 has to leave there, so they have more free access to get in and out of the cell. Other things like ions, especially your sodium, your calcium, your potassium, the stuff that's going to be absolutely essential in the cell, but yet needs to be regulated, because if not, bad things happen, and you will learn about some of those bad things. But here you have a concentration gradient or a diffusion gradient. It's going to want to come this way, but it can't. It needs to have a carrier involved. How will this carrier work? Well, if you could take this, for example, say this is a protein that's positioned like this, and as such, is sitting there and has a certain chemistry associated with it. And as it is sitting there, these guys are diffusing into here, in other words, reacting with this protein. And say there's just to illustrate the point, a 2-passenger limit here on this one right here. When they actually get in here, they will bond to these sites. They have very specific sites. I told you specificity was important. They will get into this site, and when they bind to this carrier molecule, what they do is they change the entire chemistry now. All of that stuff is redistributed, the charge and the bonds and all that kind of stuff, to where they actually change the chemistry of this molecule enough to make it want to achieve some stability that it doesn't have now, and the only way it can do that is to sort of flip its shape when it does it. Okay? I know there's a lot of chemistry involved there, but just try to take that for what it's worth. Realize the chemistry changes to the point where it needs to flip to be happy now, to achieve stability. So what you see is just that. It'll actually spin around. Okay? And notice which way it's pointing now. It's pointing in. And once it achieves stability, and once it's pointing in, it no longer has an affinity to that which it was holding. So they are released, and they let go. And guess where they're going to go? To the inside of the cell now. Because now, this is the diffusion gradient. There's still not a lot of this in here, so naturally you're still going to want to keep moving this way. Okay, do you buy that? Follow it? Okay. That's not too hard to swallow. It gets a little trickier. Okay. All this graph is showing is that if you had simple diffusion down a concentration gradient, you would see that diffusion, the amount of diffusion just continues to increase the higher that this difference is from one side to the other. There's no limits on it. There's nothing controlling it. except for concentration. And where we're different here, just so you make sure you understand, I've already said this, so this is nothing new, but transport molecule. You reach a plateau. This has to do with saturation. You can increase diffusion. You can create this big gradient, and you can increase the diffusion, but once all your carrier molecules have been occupied, you level off. You can't reach a faster rate of diffusion than that because you can't handle any more than that because that's all the carrier molecules that you have because it's saturated. They're full. Okay, now, how would a similar situation, just like we talked about, could also happen, but it could be active. It could require energy to make these things flip. Okay, and where you're going to find this, and the reason that it causes energy, is, where you're going to see this happen is you're going to see it in a situation where you've got to push things into a closet and shut the door. Right? I've used that analogy already. You got to go against what would normally happen. If you would open it and everything would fall out, how are you going to push everything back in? You're going to have to use a lot of energy, position it just right, cram it, shut it, and load it up so that if any given time you wanted to booby trap somebody, when they open the door, it would fall on them. It's ready. It's cocked and ready to go. Okay? This is what our cells do. They take sodium, they take potassium, and they cram it up on one side to wait to be able to use it when they need to. So it's like a cocked gun, ready to go. And we spend a ton of energy doing this. We're going to use active transport to do this. We're going to use carrier molecules, but we're going to supply a lot of energy because we're going against diffusion. Diffusion wants to take us from a place of high to a place of low. What we're going to do is push that uphill. We're going to go from a place of low and cram it into a place of high. Obviously, that's going to take energy. I'll show you how. Okay? Take a look at this. Crap everywhere, right? Just let's take it down into little pieces. We've seen this before, so you know what this is the plasma membrane, and you know this is one of those carrier molecules I was talking about. How is this different than we talked about last time? Notice a phosphate group right here. Notice how that phosphate group got there. Here's ATP. We've already learned about how ATP is made. Now it's going out into the cell all over the place, and all of it's being used. Here's one way it'll be used. It could donate one of these phosphate groups, adenosine triphosphate. It has 3 of them, right? So when it loses one, it becomes ADP, adenosine diphosphate. If it loses another one, it's adenosine monophosphate. That takes us to second messenger systems. We talked about cyclic AMP and adenosine monophosphate. Yeah, it's all coming together. ATP can be burned, and it would release its phosphate. Okay? It would be ADP, and now ADP will get recharged, and it'll grab a phosphate somewhere else and become ATP again. But let's look at this. Notice that what we want to do, notice our concentration gradient. It's high out here, it's low in here. But what we're trying to do is pump it out. We're trying to go against our concentration gradient. How are we going to do that? We're going to have to just rely on chemistry, because diffusion won't happen. It's not going to do it for us. We're going to have actual chemistry that will lock things together. So in this particular case, when this carrier molecule becomes what's called phosphorylated, in other words, the phosphate group attaches to it, when it becomes phosphorylated, it changes its chemistry to the point where now it is receptive and will bond to these things in here. Okay? These things like sodium, potassium, whatever. This is just a generic example. Whatever this is, previously it wasn't bonding to it. When it was phosphorylated, now it changes its chemistry to where it's a little bit different, to where now these two things are attracted to each other. Okay, these things and this carrier molecule. So what happens? This all happens in fractions of a second. So the instant that this forms, these guys stick in there. And the instant that those guys stick in there, the chemistry of this thing changes. Okay? The second that that changes, this plops off, and this spins around, all at the same time. Now, the fact that that is no longer phosphorylated, what does that mean? It is no longer chemically attracted to that thing that it was holding, right? So that means it falls off and it goes to the outside. And then immediately, this all happens so quick, the second it does that, it flips right back around and becomes phosphorylated again. Okay? So when it becomes phosphorylated, then it's attracted to these guys. Actually, well, we'll think of it like that. There's a lot of things I skipped. But there's phosphorylation here. These guys are attracted to that under this condition. Almost the second that this condition appears, it changes the chemistry to the point to where these flip around. This carrier molecule flips around, releases this in the phosphate group, sort of almost simultaneously. It happens so fast. And then the instant that happens, now you're back to square one, and it gets phosphorylated again. Okay, so you have to require energy in order to do this, energy in the form of ATP. So that's how you can cram it against a concentration gradient. In the other situation we had, this thing was more attracted to, it was just open, and it was attracted to out here where the concentration gradient was high. And then once it got bound to that, it changed the chemistry till it wanted to flip and brought it to the inside. This is the reverse of that process. Okay, this is how we can go uphill instead of downhill. This is going to be huge. We're going to talk about a sodium and potassium pump, for example. Maybe you've heard of that in your A&P. Sodium-potassium pump, we spend 2/3 of our ATP, over 66-67% on average, maybe more, jury's out, resetting this pump. That's what we do with most of our energy that we ever make, is building up these levels and pushing these, cramming this stuff in the outside and in the inside of these cells, separating these things, the sodium and potassium. Okay, so for example, if you take this, notice the sodium are the blue dots, the potassium are these little triangles here. Sort of what you need to realize at any given time is that what our body is trying to do is hoard up potassium on the inside, hoard up sodium on the outside. Make note of that. Don't forget it. Yes. Okay, potassium, we want to hoard up potassium on the inside. We are hoarding up sodium on the outside. So what we have at any given point, when the trigger is pulled, i.e. a nerve impulse, whatever, when the trigger is pulled, instantly, whoosh, you get this massive influx of sodium, and you're going to end up getting an efflux, which is the opposite direction, of potassium based upon their diffusion gradients. Okay? You're setting that up so that it happens immediately whenever it needs to happen. Okay, so what are the pumps that drive this? How do you keep pinning up that sodium on the outside and hoarding up this potassium on the inside? We have this, active transport, the same type, a carrier molecule situation. When it becomes phosphorylated, notice what it's attracted to, right? The sodium. Sodium is constantly being concentrated on the outside of the cell. Potassium is being concentrated on the inside of the cell. So it can't be free diffusion, otherwise sodium would come rushing in until it balanced out. Potassium would go rushing out until it balanced out, and then you would have a gradient at all over a period of time. We've got to maintain that gradient. It's like potential energy. We've got to maintain that gradient so that we can use it to our advantage any second that we need to. Okay? So how do we do that? Again, a phosphorylated form would be attracted to, would cause this molecule to have an affinity for sodium and not have an affinity to potassium. So you can see where that would work. The second that these guys switch, it flips instantly. This detaches, and what happens is now the affinities switch. In the non-phosphorylated form, there's an affinity for potassium. There is not an affinity for sodium. So sodium doesn't stick to it. It gets dumped out here. Potassium wants to stick to it. And then the second that happens, it's phosphorylated again. You flip back. Potassium dumps out. Sodium goes in. It dephosphorylates, flips around. They switch again, and it just goes over and over and over in fractions of a second. And you're pumping. You actually pump more sodium than you do potassium. Okay? You'll pump out 2 sodiums to the outside for every 3 potassiums that you pump to the inside. Okay? A way to remember this is, I don't know if you have any experience with the periodic table or not, but sodium is a smaller atom than what potassium is. So naturally, smaller things tend to move a little bit more quickly. Okay? So think of it like that. If you look on the periodic table, you'll see the number associated with sodium is a lower number than the one for potassium. That means it's smaller. So you're going to move accordingly. All right. Other kinds of assisted transport. Okay. We can use vesicular transport, which are little bubbles that form that surround stuff. They can float through. You can make a specific vesicle for something. Say it's like a protein, for example, that's budding out of the Golgi body. It buds out, it gets wrapped up into a little membrane, it can float around the cell. That's vesicular transport. If you have to exocytose something out of the cell, that's how it's going to happen. These little bubbles are going to float up to the plasma membrane, they're going to fuse, and they're going to open. And the opposite, if you're going to endocytose and bring it in, you're going to make a little bubble around it. I suggest very strongly that you look at these websites on your own. They will set into motion some of these explanations that I just said. It'll allow you to see them play out. You'll see these pumps move, and you'll see these ions move, and maybe that'll help clarify than just looking at it, just unanimated on the board. Okay, so make sure those should be in the notes. If you go to the web page, and like I said, remember I told you that if you go to my web page, at the top, if you look at the lecture notes, I've also got folders with all the chapters in it, and those are HTML files. Those are just web pages. So you don't have to print all this out and load up all the PowerPoint. Just open that one and find the web page that's this slide and click on it, and you can just follow the links that way. Okay? But I do suggest strongly that you look at these. When you get down here to this site here, it'll show you sort of membrane-assisted transport. It'll give you examples. I think it goes through sodium-potassium pump and how all that would work. So you'll need to know that. Okay, now, like I said, what was the point of all of this? What is the point of moving these things around, especially in terms of active transport and loading up these sides? And it has to do with membrane potential. Now, this is going to become very important from here on out. We are setting up potentials. In other words, diffusion gradients across the membrane. If you have a lot of something here and there's less of it in the cell, you've created a potential where it wants to flow from here out the cell into the cell. Or vice versa. You can load it up the other way. By creating these potentials, you control the movement, is what you do. That's how your cell controls movement. It creates potentials so that diffusion gradients exist, and that's how it controls your movement. It tells what to go where. Okay. Now, you'll also see that when we get into muscle physiology and neurophysiology, these potentials are of crucial importance in terms of propagating a nerve impulse. I don't know if you remember like that whole impulse whenever it talked about like sodium rushing in, potassium rushing out, and it created this little wave going down. Well, we're going to look at that in much more detail. And we're going to look at how these potentials go into that. What is it? Sort of like if I asked you, if you went to a sporting event, like a baseball game, and you were in the stadium, and the wave started, right? And everybody started doing the wave. What is the wave? Tell me. What is it? What is a wave? What is the wave? Can you define that? Is it anything in itself? Is it an entity? Or is it just something that we call a certain event of other things that are happening? See what I mean? Yeah. What you've got is Well, if you think about what's happening in a baseball game, you've got people standing up, the next guy stands up, the next lady stands up, whatever. The wave itself is nothing. All it is a way to classify the behavior that you see of certain things that are moving. That's what a nerve impulse is going to be. It's what you're going to see. You're going to see that propagated impulse, it looks like an electrical charge, and it is, but electricity is the movement of ions and the movement of electrons, the movement of charge. You're going to see that potassium and sodium are going to be moving, and they're going to be fluctuating, and that is what's going to create a wave, a nervous impulse, a wave that we're going to be talking about later on. Okay. Now, keep in mind, too, and I mentioned this, but not only in terms of numbers of, like, for example, how many sodiums do you have here, how many sodiums do you have here. If you have a lot here, a few here, you're going to have a potential difference. Not only with the quantity of the things involved, but also you can have a charge potential. You can have more positive charge in one area, more negative charge in another area, and as such have electrical potential. Okay? Like in this case, if you added up the positive and negative charges associated with either side of this, let's say, membrane here, you'll see that there's the same amount of both on either side. There is no electrical potential here, no flow of electricity from one place to another. In this case, however, notice that in both cases there are 10 negative charges, but there are actually more positive charges over here. We would actually say that this is more positive than this direction, so you would see a flow of positive charge from this side to that side. Does that make sense? Where this plays out in the cell is what tends to happen because of everything that's going on is we create this potential in our cell to where the inside of our cell ends up being slightly more negative compared to the environment. Okay? Outside of our cell, especially because we're pumping out so much sodium and that kind of stuff, you have a little bit higher of a positive charge, especially right near the surface of that cell. and a little bit more of a negative charge on the inside of the cell. So the cell is negative, usually, compared to its environment in terms of charge, in terms of electrical potential. This is going to be very important. Okay, so before we get into all these pictures, we're going to look at the sodium-potassium pump. It works like an active transport pump that we've already talked about, but I want to just sort of elaborate a little bit more. Again, I told you it transports more sodium to the ECF than potassium. Okay, it's a 3-to-2, 3 sodiums for every 2 potassiums. And one other thing to note is that what you've got to keep in mind is, yes, there are channels that are very specific to certain things. But not every single one of your channels and carrier proteins that are on your cell membrane, not every single one of them exert maximum control and just block and then let go and only block and let go whenever told. Sometimes there's what's called leak channels. You may have a potassium leak channel that's sort of like a vent. And it will allow, as long as potassium wants to go, it'll allow it to go through. There's no control over that. The only control is that only potassium is allowed to go through. That's the only level of control that's exerted. So we do have leak channels. So what you've got to sort of keep in mind and think about in your head is that all this stuff that you're going to see as things are moving in and out, it's very dynamic. Yes, there's more sodium on the outside of the cell, and when it comes rushing in, what you see is a big rush of sodium, but at the same time realize there's some sodium rushing out because some of it's leaking out through that channel. So it's sort of like there's a whole bunch going this way and a little bit going this way, and the difference between them is your net change. Okay? Same thing for potassium, same thing for calcium, same thing for everything that we're talking about. But one thing that I will point out at this stage is when everything's loaded up, and I mean like when the gun is cocked and it's ready to go, and you have a whole lot more sodium on the outside and you have a whole lot more potassium on the inside, and they're ready to diffuse if the channels ever open up and just have a free-for-all and everybody can move. Under those conditions, just by virtue of the chemistry associated with this cell, the plasma membrane allows potassium, it's more permeable to potassium than it is sodium. It's easier for potassium to leak across than it is for sodium. Okay? So that's sort of something that we have to deal with as all this stuff is moving. I'll show you how that plays out the farther we go. All right. So what we've got here is, sorry, let me make sure there's nothing else I want to say. Okay, so before I move on, realize this. It says the concentration gradient for potassium. Okay? There's a big K here, a little k here, because there's more potassium, like I said, on the inside than there is the outside. So this is the normal concentration gradient. It wants to go this way. Okay? Now, I also said, remember, that in the other picture, as far as the electrical gradient, it's a little bit more positive on the outside, a little bit more negative on the inside. So let's keep in mind that. Here's the electrical gradient. The electrical gradient is more positive out here, more negative in here. Now what does that mean for potassium? Look what charge potassium has. Potassium has a positive charge associated with it. So it's one of those positives. So once it's out here, electrically speaking, what it wants to do is be attracted to this side of things. Okay? Now its concentration in terms of the actual atoms that are there. The atoms, there's more of them here than there is here, so here's its concentration gradient, but its electrical gradient goes back the other way. Now there's too much. Too much to think about, right? And it's true. There is a lot to think about. But hopefully we can start putting it all in motion here in a second when you see it all happen together. Hopefully it'll make more sense. So you've got concurrent sodium and potassium movement. Okay? You've got potassium naturally wanting to diffuse out. This A stands for large anionic things. These are like proteins, biological molecules that are locked in the cell. They can't escape. Okay? They tend to have a little bit of a negative charge to them. That's why it means they come up here and they can't make it out. So that's why they're sort of just denied. And that's part of the reason you get this big negative buildup in here too. Okay? So here's your gradient for potassium. Notice the sodium gradient is the opposite. Since there's a whole lot more sodium out here, the big letters here, a lot less sodium in here, naturally it wants to travel that way. Okay? That's the way it's designed to do now that we've loaded it all up through that pump. Now we have a potential. Where by doing this, by locking up this potassium in here, by locking up all the sodium out here and holding them and forcing them to stay apart, we now have a potential that we can utilize. Okay, we can cause things to happen. Okay. You'll also notice that wherever Na goes, usually Cl follows for chemical attractive purposes. Okay? So that's why it says and dissociated Cl. If sodium comes rushing through, chances are chloride's right behind it. It's going to go with it. Okay, so here's what we've got. We've got, here's the ICF down here. Here's the ECF. I told you that we have active sodium-potassium pumps working that are being phosphorylated. It's not shown here, but they would require energy. And in so doing, they are taking sodium, shoving it out. They are taking potassium and shoving it in. Okay? At the same time, what we have here are these passive channels that is allowing this potassium that's hoarded up in here to sort of leak back out that way. And you've got sodium channels that are allowing some of this to leak back in this way. Okay? All right, but still, not as much of this is happening as what you are creating over here. Does that make sense? You're still loading up. You're still maintaining a difference on either side, even though some of it is always leaking on to one side or the other. Okay. Now, your nerve cells and your muscle cells are going to make special use of this potential. You will see that certain of these protein channels, for example, they have little gates on the bottom of them that only open under certain electrical conditions. So once this stuff starts moving, all of a sudden, gates that were closed can now open because of an electrical change, and then a mass influx of stuff comes flying in, and that's an action potential. Things start. We'll get that to Chapter 4. This is enough for Chapter 3. Okay? I believe that's the end of this. So I finished early. I'll tell you what I will do, though, since we've got some time. I want to go back. I want to take a look at some of these animations. Okay? Let's go through these in case there's anything I want to talk about. You certainly don't have to. I mean, if you do whatever you want, it's your grade. Was that the first animations I had? Okay. So let's do these. Any questions before I start? Multiple choice. Yeah. There's typically around 70 questions. Do your study guide. Around 70. Well, those are not the questions that are on the test. All that material. The point of that study guide is to, now that you've had chapters 1, 2, and 3, and this is your first test, and some of you have never taken a test with me before, and if you have, perhaps it's a class different than this one, which is drastically not going to be the same. Sometimes it's a little overwhelming, and you're thinking, how do I study this? There's way too much stuff to study. How do I know what I'm going to stress, for example, on the test? That's why that study guide is there. Study guide tells you what I think is important and what you need to be sure to look at. And if you use that as a guide and you can answer those questions, now realize some of them are going to be longer answers than others. Some of them may be a one-word answer. Some of them may require like a few sentences of explanation or more. Realize that I'm not going to ask you those questions, but I'm going to ask you questions about all of those topics that are on there. That's what a study guide's for. Study guide's not to give you the answers to the test. Okay. Now, realize, hang on one sec. The way the test, I'll just give you a little bit about the test in general. The tests are hard. Okay? I'll tell you straight up, they're hard. And the reason that a lot of it's hard, what you'll see is, and it's not for me just to be mean, because what you'll see is I'll renormalize. I don't call it curvy, but I renormalize. So if the class average is, say, like a 68, and I want it to be a 72, I'll just bump the whole average. I'll shift the whole curve up 4%, something like that. Okay. So as far as competition-wise and everything like that, it's fair. Okay? You're all in the same field. But the questions are going to be, you'll see that the wording, it's not like I'm intentionally trying to trick you or anything, but you'll have to look at some questions and say, okay, now wait a minute. And you'll have to think about this, and the point is to go a little deeper, and it'll be challenging. I promise, I won't let you down. But at the same time, I also promise that it will be fair if you do this study guide. Okay? So there should never be a case where you do it. If you do the study guide and you come in and say that test was completely unfair and we didn't talk about any of that, you're going to be wrong. Okay? You won't have much of an argument. I tell you what you need to know right there on that paper. Whether or not you want to do it's entirely up to you. And it's not going to be easy. If you've been working on that study guide, you'll see that it's not something you can sit down and do in 15 minutes. Okay? You should be working and chipping away at this study guide from the second we start. Okay? As soon as this test is over, I start with Chapter 4. You get your notes out, you get your study guide out, and as I'm lecturing, if I answer any of those, do it. Okay? As you see a slide, know what those questions are and keep chipping away at it so you don't have all of it to do right before the test. Okay? I try not to, I know how confusing those are too. I try not to do any of those questions where it's like A and B, A and C, A and D sometimes on Thursday, E none of the above, because then, that's just way too confusing. It does, and I try not to do that, but sometimes there's just not a way around it. Sometimes the question is such that I have to ask it like that, but I'll try not to make a whole test full of those. Okay? There will be some all of the above, none of the above, just because, you got to think about what I've got to ask you and that kind of stuff. So, which of the following ions are involved in this? Obviously, there's probably going to be a none of the above or all of the above choice on that one. It's kind of one of those things. Like I said, about 70-some, it'll range. It may be low end, like 60, high 50s, 60 questions, high end 74, 75 questions. Typically, are somewhere around 70 questions. So, expect. Huh? Yes, it'll be a Scantron. Okay. Anything else? Yeah, sorry, I forgot. Now remember what I said about the homework. I'm only going to grade 3 of them. I'll give you best out of 3. You get 2 out of 3, you get full credit. You get 1 out of 3, you get half credit. You get 0 out of 3, you get no credit. Okay. If you only put true and false, that's all you give me to grade. That's all I'm going to grade. Okay. There are true-false answers to this that I have deemed as true and false. However, some of them are argumentative, and you can make a case for it. If you want to explain your reason for putting what you did, regardless of what the real answer is, as long as what you say makes sense and I see why you put what you did, then I'll give you credit for it. Okay? It won't be a big deal. I'm not trying to get anybody or anything. Okay? Now, that does not mean that I want a 500-word answer for 15 questions. That's ridiculous. You don't got that kind of time. I don't got that kind of time. You got better things to be focusing your time on. Okay? They shouldn't lend themselves to that. But if you have questions, ask me. That's what I'm here for. If you want clarification on something, ask me. But some of these things will be very easy, and there is a straight true false. You can just put true, and don't have to worry about explaining it. Or you can doubt yourself and just change a couple. Even if you change a couple words, like if you want to make it something else and it's confusing, so you mark out this word and you put this word in instead. So I see that you've rearranged it to a true false statement that now, that's fine too. Okay, that's fine too. Now just don't rewrite 15 questions and make up your own questions and make an answer to them. That's not going to cut it. Okay, you can't do that. Anything else procedurally about any of that? Okay. First one's always the hardest, right? Because you don't know what to expect. I understand that. But realize I've never had a class where, I've had 50% of the people fail. That's not going to happen. Okay? You'll do fine. What's that? Index. What are you going to put on an index card really that would help you? Actually, I know, because I took as an undergraduate, I took make sure I'm off. Yeah. Okay.
Organisms are not isolated systems at equilibrium.
This is sort of an overall review here. This is all I got left. So. Huh? No, I turned my mic off on purpose there for a minute. I turned it back on. You should be good. I did. I said, hey, okay. Yeah. All right, my bad. All right.
The lipid bilayer is fairly permeable to a few small uncharged molecules, such as oxygen and carbon dioxide. However, the lipid bilayer component of biological membranes is very hydrophobic and therefore retards diffusion.
So notice what can pass and what can't, right? I told you CO2, O2 can freely. Your ions, your positive, your negative charges, glucose, water, have to be controlled.
Cells have developed other means to move these compounds across their membranes. The hydrophobic barrier that characterizes biological membranes is predominantly due to the two layers of nonpolar fatty acid tails found in the interior of the lipid bilayer. Hydrophilic polar groups are found on the exterior of the
This charge means they're attracted to water. These don't have a charge. They're not attracted to water down here. That's why they position themselves the way they do. Where am I? Oh, you can do this. Yay.
However, a membrane of a living cell is much more complex than a simple phospholipid bilayer. Biological membranes also incorporate other types of lipids, including cholesterol and membrane proteins. Integral membrane proteins span the membrane, while peripheral membrane proteins are bound and exposed on one side only. Many membrane proteins are glycoproteins, which possess covalently attached carbohydrate chains. Many of these proteins found embedded in the membrane are involved in transporting ions and small molecules across membranes that do not cross readily by passive diffusion, either because of their hydrophilic nature or because they would be moving against a concentration gradient. This process is termed facilitated transport. There are two types of membrane transport, passive and active. Keep in mind that the major difference between these two types of transporters is whether they require an input of free energy to function.
You can also see specificity there, right? That glucose has to find the right one.
Passive transport can be thought of as accelerated diffusion. Transporters simply allow the passage of molecules across the membrane at a much faster rate than would occur through normal diffusion, thereby bringing about an equilibrium more rapidly. Because of this, passive transporters do not generate a concentration gradient for a compound across a membrane, but can only dissipate the gradient.
Okay, that's important. Understand what they just said there. Passive transport, because it does not require energy, it can only go with the gradient, right? All it can do is dissipate the gradient. In other words, spread it out and take it where it needs to go. It cannot create a gradient. Only active transport with ATP, the burning of ATP and moving those molecules, only that can create a gradient on either side.
Passive transport can be facilitated by transporters that provide passageways across the membrane of the right size and environment for a particular compound to cross. These types of transporters are often referred to as pores or channels. Ion channels are more complex than pores, generally requiring more than one subunit to form a membrane passageway.
You don't need to know any of this.
Additionally, while pores are formed from membrane-spanning beta barrels, ion channels commonly span the membrane with alpha helices. Shown here are two different
I would have skipped that one.
Some transport proteins do not have a channel or pore, but instead bind molecules very selectively and change their structure to allow them to pass to the other side of the membrane. These bind and release conformational
Notice the terminology up here.
can be classified as either uniport, symport, or antiport, depending on the number of types of solute molecules transported in the respective direction of transport.
So uniport takes one to go from one side to the other. Symport means two of them can go through at the same time. Antiport means two go through at the same time but in opposite directions. That's just some terminology. I don't know. You don't have to know them, I don't think. But I don't know if your book talks about them or not. I would just point it out. Well, yeah, but for the animation at hand. So.
The hydrophobicity of membranes is a barrier to the movement of hydrophilic compounds and ions into cells and organelles. To circumvent this problem, cells produce membrane transporter proteins that facilitate the movement of these lipid-insoluble molecules. Passive transporters accelerate diffusion, moving molecules across the membrane with their concentration gradient towards equilibrium. Active transporters use free energy to move molecules against equilibrium, generating a concentration gradient.
Okay. Now, keep in mind also, actually, I forgot what I was going to say. Now I'm looking at this. Must not have been too important. I've already told you. If I think of it, I'll tell you. Yes. Active transport will always create a gradient, period. Well, it's going to be working from low to high, and in so doing, creating a gradient. Because if it's working from low to high, it's creating and maintaining a high concentration here and a low concentration here. Passive would just take what's there and move it and sort of dissipate it and allow it to sort of balance out. The only way you're going to keep it unbalanced is by using energy to force it in one direction and maintain a difference on either side. I think this is sort of the same stuff.
Such as sugar and amino acid can be transported up a concentration gradient. The sugar moves via a membrane transport protein from outside of the cell where the sugar concentration is low to the inside of the cell where the sugar concentration is high.
Okay, also, that's what I was going to... you may also find that when you do the study guide that there will be a couple questions on there that I don't necessarily cover directly in lecture, but you can find in the book. That's part of the perks of doing the study guide. Okay, so, but there won't be anything on the test that wasn't covered in there, okay, in the study guide.
The transport of the sugar through a coupled transport protein is driven by the movement of counter ions, such as sodium ion or proton, that are moving down their concentration gradients from a region of high to low concentration. Sodium ions and the specific sugar or amino acid simultaneously bind to the same transmembrane protein on the outside of the cell, called a symport. When the counter ion is sodium, the low concentration of sodium on the inside of the cell required to transport the sugar is maintained by the sodium-potassium pump, which is powered by ATP.
At the same time, all this is going,
In a related process,
you've got leak channels allowing some of that to leak out.
the inward movement of sodium ions is coupled with the outer movement of another substance, such as calcium ions. As in co-transport, the sodium ions and the other substance bind to the same transport protein, called the antiport, but in this case, they bind on opposite sides of the membrane and are moved in opposite directions. The low internal sodium ion concentration is maintained by the sodium-potassium pump.
So it's got to work faster and harder to work against all that leaking kind of stuff that's happening. So because you're moving more sodium, through a sodium-potassium pump, you're moving 3, for example, and then in that antiport situation, you're moving 1, you actually can still stay ahead of the game. You can still keep more sodium on the outside than what is coming back in. Okay? That's an example of one. Yeah, there's a bunch of different kinds. There's symport channels, there's antiport channels, there's just some that are specific for only sodium, but that's an example of one where that would happen. Yeah. What I mean by that is there's no control other than the fact, if they're present, like over here, when you have this over here, you've got to have ATP to make that happen. Your body is controlling that. Without the energy, it cannot force things where they need to go. In these situations over here, doesn't require energy. Nature's going to take its course. As long as there are atoms present, you're going to get a reaction, and they're going to move accordingly. Well, it's just not listed there. Yeah, it could. Yeah, it doesn't mean that at that specific channel chloride's got to come in with it. But overall, when you look at the big picture, when you see a movement of sodium in one direction, you generally will see at a cellular level chloride movement in that same direction. It may not happen via the same channel necessarily, but it's happening overall in the same direction. This is the pump right here. This is sodium and potassium. That's the only thing that's going to move through there. Yeah. Let's look at that a little more closely. The sodium-potassium pump.
The sodium-potassium pump is an active transport mechanism that is driven by the breakdown of ATP and works through a series of conformational changes in a transmembrane protein. 3 sodium ions bind to the cytoplasmic side of the protein, causing the protein to change its conformation. In its new conformation, the molecule becomes phosphorylated at the expense of a molecule of ATP. The phosphorylation induces a second conformational change that translocates the 3 sodium ions across the membrane. In this new conformation, the protein has a low affinity for sodium ions, and the 3 bound sodium ions dissociate from the protein and diffuse into the extracellular fluid. The new conformation has a high affinity for potassium ions, 2 of which bind to the extracellular side of the protein. The bound phosphate now dissociates, and the protein reverts to its original conformation, exposing the 2 potassium ions to the cytoplasm on the inside of the cell. This conformation has a low affinity for potassium ions, so the 2 bound potassium ions dissociate from the protein and diffuse into the interior of the cell.
Then now it starts over with more sodium. Happens in fractions and fractions of a second. That is correct. That is correct. In this pump, in the sodium-potassium pump, right. Yes, yes, yes. I don't think we need to look at endocytosis and exocytosis. But you'll also see proton pump. I'm not going to show you that either. But proton pump works the same way in terms of moving protons, which are synonymous with hydrogen ions. Maybe like in the kidneys and in other types of cells, you may see where we've got to create a gradient to move hydrogen ions to a certain place. For example, think about the electron transport chain, or back to oxidative phosphorylation. We had to cram those hydrogens up into that membrane space so it could diffuse back through and spin that ATP synthase and create ATP. Okay? If you don't remember that, look back at those pictures that I talked about. You're going to have to know that. Whenever that happens, there has to have been energy. Now, in that case, it wasn't so much burning ATP as it was using the electron. Remember we said the NAD and FADH picked up those hydrogens from the Krebs cycle and took them over to the electron transport chain. And what happened was the electron got stripped away from that hydrogen, and that electron was then passed from one chemical to another and releasing energy that would cause the driving of this pump. In that situation, you could take hydrogen and force it up into an area against its will, sort of like what you're doing with sodium and potassium, except we weren't using ATP then, we were actually using electrons to do that. Here we're using ATP to spin that thing around, make it go where it needs to go. The what? The final electron acceptor? Oxygen. Final electron acceptor on the electron transport chain. That's where the buck stops.